right, greetings. It is 1 o'clock on Friday. Let's get started. So NMR, you can probably tell already from having watched those videos, there's a lot more information in an NMR than there is in mass spec or IR. However, we are going to tackle NMR over 2 weeks instead of 1 day like we did for IR or mass spec. So we are definitely going to stretch this out. I want to start off with showing you what an NMR looks like, big picture, and tell you what we're going to be doing next week, and then go backwards to what we're doing this week, and then we'll go backwards to what we're doing today. So this is on your screen right now. This is outcome 3. So this will be your quiz that you take a week from Wednesday, so 11 days from now or whenever that is. And what our eventual goal is to do with NMR, what we do for IR and mass spec, which is to be able to look at an entire spectra and say, what does this mean for the molecule? To take this and tell me what the molecule looks like, this is really a puzzle with multiple pieces. And each of those individual pieces has a lot of different information that it tells you. So looking at this spectra, you can see this is chemical shift in ppm, which you should recognize. You can see that there's kind of 4 different signals. These are split into multiple peaks, but that's something that we'll talk about on Monday, so don't worry too much about that right now. You can see some are taller or shorter, having greater or lesser integrals, which you heard about in the video as well. But basically, the way that you would do this is you would need to say this part of the spectra, in other words, this first signal, tells me about one part of the molecule. This part of the spectra, the signal, tells me about a different part of the molecule. And these two tell me about another part of the molecule. So you would need to interpret each of these individual signals into a puzzle piece. And then you would need to put all of those puzzle pieces together to figure out the structure of the overall molecule. So that's something I expect you to be able to do in 2 weeks. What we're going to work on this week is basically interpreting one signal at a time. So this week, we're going to work on, this week being today, Monday, and then quiz on Wednesday, is going to be looking at just one individual signal. So if I were to ask you, Chloe, there is a singlet at 3.24 ppm that integrates to 3H. What is that? You could tell me what that part of the molecule is. We'll worry more next week about how to put all of that stuff together and a little bit about carbon NMR, but that's where we're going to. So the reason that you guys don't have a lot of spectra to look at today is that there's a whole bunch of stuff that we haven't even gotten to because there's a lot to it. So for today, we're going to look at just one at a time, starting with a molecule and going towards, well, what is the signal going to look like? But really what we want to be able to do is to do this backwards. So I know I asked you guys to predict chemical shift, which is usually one of the most challenging things to do when you first start off with. I want you to not sweat it too much in terms of getting the number exactly right, because the real skill that you need to be able to do is to say, if there's a peak at 3.24, what could that potentially be? So we need to be able to do some of the, here's a molecule, where will the peak show up? But really, it's just that we need to do that forward so that we can do it backwards. Does that make sense? So don't sweat too much whether or not your values are exactly right. It's why I always recommend look for a range. Think about it in terms of a range. I will never ask you to draw an NMR. I will ask you to be able to look at an NMR and figure out what it tells you about the molecule. All right. So let's go to our go to our bridge. Did you guys have any general questions on the videos or about the bridge in general? Before we get into specifics? No? Okay. All right. Assuming you turned it in 20 minutes ago or earlier, I went through and looked at all those and gave you guys feedback. If I crossed out a value and put a little up arrow, it means that the real value should be higher than that. The little down arrow means that the value should be lower than that. But we'll go through all of these kind of one at a time. And so any questions you have, please let me know. So for the first one, which was in the first video, the idea was just all about chemical shift. And I really, really recommend that when you do this and when you think about this and when you're drawing these molecules, remember that we're focusing just on hydrogens. Hydrogen NMR only tells you about the hydrogens present in your molecule. Therefore, drawing your hydrogens in your molecule is going to be really important. But equivalent hydrogens stack on top of each other. So they're basically all in the same signal. Therefore, I wouldn't recommend that you draw them all out like a Lewis dot structure. Instead, just kind of combining them into something like this is going to be probably the most efficient way to do it, because a CH3 automatically is telling you that you're lumping all of those H's together. So do that. This carbon right here doesn't have any hydrogens, so you can write it, but I would write all the carbons just to make sure I was counting and making sure all my hydrogens were accounted for. And then there's 3 hydrogens over here as well. So this molecule has 4 different CH3s. How many of them are perfectly identical?
3.
Right, so 3 of the CH3s, right? These 3 over here are exactly identical. So identical means the same thing it did when we were figuring out R and S. They're the exact same number of bonds away from the exact same things. So if we were looking at whether or not this carbon is chiral, we would say that this carbon is not chiral because those 2 CH3s are identical. They're the same distance away from the same thing. Hopefully that makes sense. That's what we're doing here. If you have any questions on identical or not identical, please let me know when we go through this, but I think that's pretty straightforward. It's a lot like what we've done before. So this is a CH3, but this CH3 is next to an O. All of these three CH3s are next to the exact same carbon. So this one is different from these. This would be environment A, and this is environment B. All right, so there are some values that I asked you to remember about just where things show up ppm-wise. So for instance, if you have a hydrogen exactly attached to a benzene ring, where do those show up? Anybody remember?
9.
Close. 7 to 8, yeah. So hydrogens on a benzene ring are 7 to 8. There is something 9 to 10. It's hydrogens on aldehydes. Benzene rings, we did benzene rings. Carboxylic acids are like 10 to 12. So there are some numbers that you just need to memorize because those are just where those things show up. Thankfully, there are less of them than there were on IR. You don't need to know their shape, just their general vicinity of where they show up. Most of those space out pretty well. The only other real one is alkenes. CHs that are part of alkenes are five to 6. Okay, 5 to 6 ppm is where a hydrogen directly on an alkene. All of the other stuff that you guys have written down that's further to the right, those are CHs that are near something or next to something. That was the whole idea of de-shielding, that there's stuff nearby that's pulling electrons away. And what is the region that's farthest to the right? So like that 1 to 1.5.
CH3.
Yep.
Carbon.
Yep.
CH2 / carbon.
Yep.
CH.
Yep. So what all those have in common is they're parts of alkanes. So alkanes are the most shielded. So if you think about nonpolar molecules, like octane, a nonpolar molecule that's an alkane, alkanes are nonpolar. Nonpolar means electrons are not more pushed in one direction than the other. The electrons are evenly shared throughout. It's this lovely sharing community of electrons, and electrons are everywhere, and all of the hydrogens are perfectly well shared. But when we start to add in functional groups, which are going to contain double bonds or triple bonds or oxygens or nitrogens or something like that, all of those other things pull electrons away from carbons or hydrogens. So they start to de-shield and push everything to the left. The farthest to the right is just alkanes. Any other functional groups start to pull them to the left. So that's why we start at the right and we're always being pulled to the left. So those are kind of regions that I asked you to remember. So a CH next to a carbon containing functional group, those are all roughly 2 to 2.5. A CH next to an oxygen and nitrogen halogen, where do they show up?
5 to 6.
Lower.
4 to 5.
Lower. Keep going, one more.
34.
30 to 40, exactly. So they space out nicely. Normally in an alkane, it's like 1 to 1.5. When an alkane's next to a carbon containing functional group, so like a carbonyl or an alkene, it's 2 to 2.5. And then if there's CHs next to an O or an N or an X, then they're like 3 to 3.5 or 3 to 4. So they're pretty nicely spread out. So there's another way to think about that, which is that the effect of an oxygen on its neighboring alkane is that it pulls electron density away by about plus 2 ppm. And so we can think of this kind of additively instead of just memorizing it. which is that normally you would find an alkane somewhere between 1 and 1.5, but if it's next to an oxygen, then it pulls it up by 2, which would result in it showing up somewhere around 3 to 3.5. And if we had memorized where do CHs next to O's or N's or X's show up, which we said 3 to 4, it's about the same thing, roughly 3 to 4, 3 to 3.5, it's about the same. I can also tell you that CH3s tend to be on the low end of that. A CH or a CH2 is more on the high end of that, but this is a pretty fine working rough region. Again, the goal of this is not for you to be able to, at the end of the day, predict and draw an NMR. It's for you to be able to take an NMR value and think about it backwards. All right, so you guys don't have on your chart anywhere, where would a CH3 be that's 2 doors down from an oxygen? So that's where this kind of thinking about it additively can be helpful. An oxygen would have that effect on its neighbor of being about +2. But that doesn't really matter for this carbon because there are no hydrogens. So if you think about it, if you live next door to really rowdy neighbors, it's going to have a pretty big effect on your life. But if you live 2 doors down from some rowdy neighbors, you'll probably have some effect, but not as bad as if you live next door. But if you had rowdy neighbors that lived 2 blocks away, you probably wouldn't even know. So that's kind of what happens with these oxygens or something that's pulling electrons away. Right next door, they have a pretty strong effect. 2 doors down, the effect is still there, but it's a lot less. So from my experience, it's about 25% of what it would have been if you lived next door. And then if you were 3 doors down, there's basically no effect whatsoever. So I think, yeah, if there was a big party a couple doors down, you might or might not notice. It might or might not wake you up at night, but if it was right next door, it'd be a big effect. So 2 doors down, it's about a quarter of that effect. So oxygen pulls really hard on its next door neighbors, somewhat on its 2 doors down neighbors, and then really it's too far away to make a difference when it's past that. So I would approximate that the effect of the oxygen on 2 doors down is about a quarter of its effect that it is on its neighbor. So a quarter of +2 would be a half. So it might have the effect on these guys of being about +0.5. So once again, saying that our alkanes would be normally 1 to 1.5, we'd add a half to that. So where would you expect these guys in environment B to show? Just shifting this whole range by about +0.5. Yeah, somewhere kind of 1.5 to 2. So here's how this is not the end of the world with this 2 doors down thing. A CH3 is normally going to be 1 to 1.5, but CH3s are usually at the low end of that. So I would predict that a CH3 is normally going to be around 1. But if it's moved up a little bit, it's going to be maybe 1.5. But whether you put these in the 1 to 1.5 region or the 1.5 to 2 region, they're all roughly in the same-ish area. They're not at 7. And they're not at 0.4. But if they showed up at like 1.4, that's there. If it's like 1.6, it's there. If it's 1.8 or even 1.29, it's roughly in that rough region, and you're getting kind of a rough idea of where they show up. And that's what I'm asking you guys to be able to do. Just get a rough idea of where they would show up. Does that make sense? So that's roughly where they would be. All right. So in this guy, let's go ahead and draw all of our hydrogens. That's a CH3. That's a C. There's a CH2. That's just a C. This one got forgotten a lot in the bridge. That's a CH. There is a hydrogen there. And then these are both CH3s. All right, Mallory, are any of those identical? Yeah, the 2 CH3s on the right are identical to each other. And then the CH3 on the left, same or different? It is different. Yeah, so this CH3 is next to a carbonyl, and these CH3s aren't, and that's all you need to, that's as far as you need to go. So there would be 4 different environments here, A, B, C, D. So we can use the letters to name them or something like, or identify them, but they're just 4 different environments. So let's start off with this one, A. So normally a CH3 is going to be around 1 to 1.5. And what's the effect of a carbon-containing functional group next door? Meaning like an alkene or an alkyne or a benzene ring or carbonyl. What do they do to their neighbors? Yeah, so they're about a +1. We can go ahead and do that. They would have a plus, both of these carbonyls would be about +1 on their neighbors. So we'll just add a +1 to that. And so I would predict that A would be somewhere between 2 and 2.5. And that's probably good enough. All right, that oxygen has an effect of its on its neighbors about a +2. So Timothy, where did you expect C to show up? This one right here.
3 to 4.
Yeah. So we did this one already. 3 to 3.5 is fine. 3 to 4 is fine. It's somewhere in that region. 3.x. All right. So D, we've done something exactly like this one before, this D, where it's 2 doors down from an oxygen. So where would we expect this guy to show up? Yeah. So instead of like 1 to 1.5, we could add a quarter to it because that oxygen is 2 doors down. So, oops, 1.5 to 2. Again, because they're CH3s, they're probably on the lower end of that, so somewhere around. All right, so where I find the little +1 thing to be pretty handy is if you have an environment that's simultaneously next to 2 different functional groups. Because if you're next to 2 different functional groups, your electrons are being withdrawn, or you're being electron point of view de-shielded in both directions at the same time. So for this CH2, we might start off at 1 to 1.5, but you're adding a +1 from the carbonyl on the left, and you're adding a +1 from the carbonyl on the right. There might be also an effect of this oxygen that's 2 doors down, but it's going to be relatively negligible compared to everything else. But you're starting off at 1, and you're really adding 1 to it twice, so you're adding 2. So you end up at like 3 to 3.5. So this one actually shows up in roughly where you would expect if it was next to an O or an N or an X, but it's because it's next to 2 different carbonyls. Those chemical shifts make sense? Questions about any of those? All right. It's a whole lot of thinking. If it's on a functional group, it's going to be in one of those special regions like 5 to 6, 7 to 8, 9 to 10, or 10 to 12. But if it's nearby something, it's probably going to be somewhere between like 1 and 4, 1 and 5. And we can go through and kind of roughly estimate it based on the electron withdrawing strengths of those neighbors. But you end up doing this a lot, +1 or +2, starting at that 1 to 1.5. All right, so let's move down here. Let's go ahead and draw in all of our hydrogens. This is a CH3. There's a carbon with no hydrogens. There's a carbon with no hydrogens. This is a CH3 and another CH3 and another CH3. All right, Yesenia, how many of those are identical? Correct. So all of these are identical. So this would be environment A, and this would be environment B. So there's 2 environments, or this NMR should have 2 signals on it. That's A there. The chemical shift is what we just did. B is right next to an oxygen. So where would we expect that one to show up?
3 to 4.
Yeah, 3 to 4, something like that. 3 to 3.5 is also perfectly fine. Point is that it's going to be around 3 something. Right? What about these CH3s over here? Miguel, what do you think?
Well, they are attached to a carbon attached to a carbonyl.
Right?
So that would be, sorry, I looked at my notes.
That's all right. The effect of a neighboring carbonyl.
The effect of being right next to the carbonyl would be 2.5. So you could be taking,
Yeah, so it's a lot less than that. It's because they're 2 doors down. So
0.25.
yeah, like maybe 0.25 higher than normal, which is not very much. So give me a rough guess.
Where the
Yeah, where A would show up.
really small math in my head.
Yeah, so normally a CH3 is around 1. And if it's 2 doors down from a carbon containing functional group, which pulls it up by about a quarter,
1.25 or 1.75?
Yeah, something like that. So kind of maybe like 1.25 to 1.75. Again, because these are CH3s, I would expect them to be on the low end of that. So maybe 1.25, maybe 1.2, 1.3, something like that. Somewhere around that rough vicinity. That make sense? Somewhere. So not exactly where an alkane is, but not much higher than that. All right, so the third thing is the relative integral. And the integral is pretty simple once you know how to do it. What is the integral telling you? Chloe, what does the integral tell you? Say it louder. Yeah, it's the ratio of what? Yes. Yes. Yeah, just how many hydrogens are in the environment. Exactly. And so it's really just counting the number of hydrogens in your environment, and that's all that it is. It's really, really helpful information. In fact, I would say that this would be your number one place to start when you're decoding the signal in an NMR, is how many hydrogens are in that environment. So an integral is probably something you first heard about in calculus because it's the area under the curve. We don't solve it the same way you do in calculus, because in calculus you're doing it when you have an equation and you're deriving or you're integrating to find the area under the curve. In our case, what we do is we basically have the spectra. It just counts the pixels under the curve. So it's giving you the same information, but it's not doing it through mathematics. It's doing it through just looking at the spectra and counting the area under the curve. And so when it does that, it's not smart enough to tell you the number. It doesn't tell you the number of pixels, right? It gives you a ratio. And so a ratio is going to be the lowest common denominator. So in this case, it should be 9:3, because there's 9 hydrogens in environment A, 3 in environment B, but the NMR would tell you 3:1, because that's the most reduced down. But this would be 9:3, which it would tell you is 3:1. When you're doing this and putting this information out, I would highly recommend that you put some units on there. So I would say 9H to 3H, because all of these are going to end up being pretty small numbers. So the number of the area under the curve is a 3 or a 9. The chemical shift might be a 3 and a 1. The number of environments is 4. And then with splitting, which we'll talk about on Monday, that's also really small numbers. Keeping track of which piece of information is telling you what about the environment is really important. So just keep track of that. Yes, sir.
I don't know if you mentioned this in the video, but do you want us to simplify it, or will you take it if we just put the back on?
You're not going to have to tell me what anything ever looks like. You'll have to be doing all of this backwards. So I will tell you what the NMR tells you, and the NMR would tell you 3:1. So if you see a 3:1, what you should do is think, well, this says 3:1, but I know it could be 6:2 or 9:3. So just be aware that the NMR is not smart enough to tell you exactly what it means. All right. So I would say keep in mind that it's all on the table that way. So this was the one where hydrogen got lost a whole bunch as well, but let's go ahead and draw them out. The far left, we have a CH3 and we have a CH2. This is a carbon. It's only got 3 bonds, so this is a CH. That one was ignored a few times on the CH3. So there are 5 different carbons with hydrogens. Are any of them identical? Yeah. So the 2 on the right are identical. So we will have 4 different environments, A, B, C, and D. So these 2, B and C, are not exactly the same. They are both going to show up around the same place in the NMR because they're both next to oxygen. So I would expect both of those to be that 3 to 4 region, but they are different, so they will show up at different peaks. Same thing is true of A and D. These are both 2 doors down from an oxygen, so they're probably somewhere around like, I don't know, 1.25, 1.5, something like that. But they are different because this is a CH3 all by itself next to a CH2, and these are 2 identical CH3s next to a CH, so they are different from each other. All right, I just gave you chemical shifts. These guys right here should be 3 to 4 or 3 to 3.5, whichever one you want to go with, but they are different. And these would probably be somewhere like 1.25 to, I'll just say plus, 1.25 to 1.75, something like that. Somewhere in that rough region. But these would all be different. So let's go through and talk about what would definitely be different, which is the integrals. So Mallory, what are the integrals on these? Start at the left. Yep. 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 Exactly. So your integrals would be 6, well, whichever way you went. They show up on the NMR in terms of chemical shift. So the scale of the NMR is the chemical shift. 1, 2, 3, 4. And so what this would look like is that you'd have a pretty big-ish peak around 1.25 and a smaller peak around 1.25. So you'd have like, I don't know, a peak there and a pretty big peak. And then a much while later, you would have maybe a 2 peak and then a 1 peak. And the areas under these curves, this would be 1, this would be 2, and this one would be 6, and this one would be 3. And so it mostly manifests somewhat in terms of how tall the peak is. It's not really about peak height. It's about the area under the curve. It just happens that if you have a lot of area under the curve, the peak tends to be taller. So, all right, that is the bridge in 20-ish minutes. Questions on that? Otherwise, we're just going to start going through some more examples. Yes, sir.
All right, I still don't quite get the I have to show you.
Oh, which one?
Where we have the regions like the 1, 1.5, the 3 to 4 and all that, but
Yeah.
then we're trying to find out the like it's +2 or +1. I don't
Yes.
know if it's +2, +1 part.
All right, so there's just basically 2 different ways to approach if you have an alkene or an alkane and it's near stuff. And so I gave you at first kind of like this, here's an NMR, here's the regions where things show up, memorize this. And so for that one, we said a CH or any alkane that's next to an O or an N or an X is going to be 3 to 4, right? So the other way to think about it, which is particularly useful if you're not just next to, but near or next to multiple different things, is instead of just remembering that next to O or N or X is 3 to 4, if you think about how we got there. So the whole +1, +2 thing is, how did we get there? So an alkane itself is 1 to 1.5. That's where alkanes are. But if it's an alkane that's next to an oxygen, it's been shifted from 1 to 1.5 to 3 to 4. So it's gone up by about 2. So therefore, the effect of that neighboring oxygen would be by moving it up by about +2. So what if you're a CH2 and you're next to 2 oxygens? Well, that's not on our chart. So the chart only takes you so far. But we can figure this out if we apply that kind of logic of how much do they change. So that's where I would say that, let's start at the baseline. An alkane is usually 1 to 1.5. Does that make sense? And then we just said, and we saw it over in here, that the effect of one neighboring oxygen or nitrogen hydrogen is that it pulls electrons away and shifts your chemical shift by about +2. What would the other oxygen do? Also +2. So where would you expect this environment to show up?
5 to 5.4.
Perfect. Yeah, so like 5 to 5.5. And so that's not, I don't think it's worthwhile for you guys to memorize every single possible situation for every hydrogen that could possibly exist in a molecule. But if you get this kind of rough idea of the effect of an O or an N or X is about a +2, or any of the carbon-containing functional groups is about a +1, then no matter how complicated the molecule is, you might not be able to predict exactly where it is, but you can get a rough idea. So that's kind of the +1, +2 thing. Does that make more sense? Okay. And then, like if you had one that was 2 doors down, it has a little bit of effect. So you can kind of add in a little bit more, and you're just kind of bumping it farther and farther and farther to the left as it gets more and more and more deshielded. So in a weird way, if you got a CH that's like next to 3 bromines, That guy shows up at like 7.27 ppm, which is where we would expect a benzene ring to show up, but it's because this thing is like 1, and that bromine has an effective +2, and that one has an effective +2, and that one has an effective +2. You add it all together and you get 7. So otherwise, it doesn't make much sense, but if you think about it in terms of cumulative effects of multiple neighbors, you can kind of get to the same place. All right, good question. Oh, how you feeling? Miguel, how you feeling? We can do this, Mike? Good? Yeah? Okay. All right, so let's look at some different examples. We will stop looking at that. Anybody out in Zoom have any questions? All right. Let's think about a molecule like let's go with this one right here. Oops. So the first thing we're going to spend about maybe 15 minutes thinking about some more examples of chemical shifts, number of environments, integrals, and then we'll do some of these backwards. So if you're trying to figure this out, what should be the first thing that we do for hydrogen NMR? Draw your hydrogens, perfect. So this is a CH3. There should be one hydrogen here, one hydrogen here. That's a CH2, and that's a CH2. All right, so Yesenia, how many environments are there? All right, tell me which of these are, so as we look at it, there's definitely 5 different things, right? Which ones are identical? So this CH right here is next to a CH3. This CH here is next to a CH2. So are they identical? No. So is anything in here identical? No. I mean, besides the fact that the CH3 is 3 identical hydrogens. So how many environments do we have? Exactly. We will have 5 different environments. 1, 2, 3, 4, 5. That make sense? All right. So Miguel, talk to me about chemical shifts.
No.
Chemical shifts. So where do they show up in terms of ppm?
So because of that bromine, CH2 would show up at 3 to 4.
Great. Yes. So I would expect that this one would be 3 to 4. If you put 3 to 3.5, that's fine as well. What about B?
B would show up at 1.5 to 2.
Well, it is next to an alkene. So I would say that what's more important than what's 2 doors down is what's directly next door. This environment B is right next to an alkene. All of those carbon-containing functional groups, meaning all of those alkenes, alkynes, carbonyls, all that benzene ring, they all have an effect of about +1. So this one, instead of being 1 to 1.5, just add 1 to that. Yeah, and it's possible that being 2 doors down from the bromine would pull it up even a little bit more, maybe another half. So it might be like 2.5 to 3, but it's definitely going to be somewhere in that 2 point something region, which is, yeah. Does that make sense?
Yeah.
So if we're trying to be complete, we would say that for environment B, it's right next to an alkene. So we would pull it up by 1. And it's 2 doors down from a bromine, which would pull it up by 0.5. So we would add 1.5. So we would end up at like 2.5 to 3. But again, I don't want you to spend all the time micromanaging this, because our goal is, I'm going to tell you where this peak is, that it's at like 2.63 ppm. And I want you to know 2.63 ppm is probably next to a carbon-containing functional group, maybe somewhere nearish to something else, but that's all you need to worry about for that. So trying to drill down to exactly where it's going to show up is not pointless, but not exactly necessary. So give me a rough region. Where's this guy going to show up? Yeah,
2.5.
sure. 2.5 to 3 sounds great. All right, Chloe, where do C and D show up? They are different. So exactly. So stop there. So these are both going to be 5 to 6. So when you are on a functional group, not near one, not an alkane near a functional group, but actually part of a functional group, then you just need to know where your region is, and that's where you are. So exactly. So this one would be 5 to 6, just because hydrogens on alkenes are always 5 to 6. The same thing for that. But what about E? E is an alkane that's next to an alkane. Sorry, an alkane next to an alkene. You do. So this is the effect of a neighboring carbon-containing functional group is about +1. So instead of being 1 to 1.5, it would be where? Yep. Yeah, like 2 to 2.5. And in your 2 to 2.5 region on that chart, you've got carbon. CH is next to alkenes, CH is next to carbonyls. They all kind of end up in the same rough region. All right, good. So that's where those show up. All right, Mallory. You ready to integrate these? All right, so starting at A, what's my integral?
2.
Yep, 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 yep. Perfect. Sound good? All right. That's roughly how we do this. Questions on that? No? Okay. All right, Timothy, you got a new one. Dun, 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 dun.
Dr. Ring,
Let's do this. Boop, boop.
Dr. Ring.
Oh, I hear you. You're not very
you're good.
loud.
I just had a quick question. Do you not have to draw the line graph with all the humps on top of each other?
You don't. So you're talking about like that this would be 2 on top of each other.
Yes.
Yeah. No, I'm never going to ask you to draw an NMR. I'm going to give you NMRs and ask you what it means. So if that, I did that to try to be helpful and show you how we got that area under the curve adding up. But all we're really looking for is what's the area under the curve. Because the information I'll give you is that this one integrates to 3H, then that's what you'll be looking at.
Gotcha. Sounds good. Thank you.
You're welcome. So in terms of actually, let me take one of these peaks and show you what you'll be asked to do on your quiz next Wednesday. So let's go with that environment E right there. Basically what I would tell you is we have a peak. It's a signal. And it would be, I don't know, 2.32 ppm, and it integrates to 2H. What does that tell you about a part of a molecule? There's one more piece of this that we'll get to on Monday, which is the splitting. But for right now, if you see those two things, what does an integral tell you? So we're thinking backwards right now. You just did it, Mallory. What does an integral tell you? All right, so it directly tells you the area under the curve, but what is that indicating about the environment? Where'd you come up with this 2H? Right. Oh, I just did it for this one. Sorry, never mind. Well, I made up a new thing. So it's not E, it's just a new thing. So, excuse me, how many hydrogens? So if there are 2 hydrogens in the environment, what does that mean about your part of the molecule? What has 2 hydrogens? A carbon with how many hydrogens? 2. So a CH2. So this thing right here, this signal is telling you that it is a CH2. And carbons make 4 bonds. So right, this was a CH2. This was a CH2. A 1H was a CH. A 1H was a CH. What was a 3H? A CH3. And we know that carbon makes 4 bonds. So a CH2 has two more things attached. Right? If you are at 2.32 ppm, what does that mean that you could be next to? Integral tells you what you are. Chemical shift tells you what you're near or next to. So we've seen a bunch of things already today that were in this like 2 to 2.5 region. So what makes a signal show up between 2 and 2.5? Well, it is a CH2. We know that because of the integral. But just look at your bridge. Which ones showed up between 2 and 2.5? What were they next to? Right. Or carbonyls. Yep, benzene rings. This is where we find CHs or CH2s or CH3s next to carbon-containing functional groups. Seeing a signal at 2.32, it doesn't tell you which one it's next to, but it tells you that it's next to one of those things. So it could be this, or it could be this, or it could be this, or it could be this, but it's one of these things. And you wouldn't know exactly by looking at that one signal which one it was, but you do know that it's a CH2, and you know it's next to some carbon-containing functional group. So don't guess if you're not sure. Be vague, because at this point we don't know for sure. So thinking about what we have done over the last week, do we have a way of knowing which one of these functional groups is present in your molecule? Not from today.
Right, from a IR.
Exactly. IR tells you if you have a carbonyl or a benzene ring or an alkyne or an alkene. So taking a 45-second break from NMR, what we did last week is still valid. The mass spec is still the best way to find the molecular formula of the molecule because it tells you the mass, which is how much stuff is there. The IR is still the simplest and most straightforward way of knowing which functional groups are present. Frankly, NMR can tell you a little bit about both of those things, but not as well as either the mass spec or the IR. So the NMR does give you more information, and you're more likely to be able to build an entire molecule from NMR than you are the other ones. But a lot of times you can't do it just on NMR alone. So all of these three things have their own strengths and weaknesses, and they go all hand in hand. So there are some functional groups we can tell from NMR, because if there's a functional group that has a hydrogen, we'll see its hydrogen. So if you had this thing right here, and there were some peaks between 7 and 8 ppm, what do peaks between 7 and 8 ppm tell you? You can look if you need to. Benzene ring. Yeah. So if you saw this peak and you know there's a benzene ring, then probably this is a CH2 that's next to a benzene ring. And you can start to put those puzzles together. But for right now, this is what we're doing, is getting a rough idea based on the information we have. All right, so we got a little bit ahead of ourselves, or I did. Let's go back to this thing real quick. How many environments do you have in this molecule? 3. Yep. So we've got this H right here. This is a CH2. That's a carbon with no hydrogens, and then this would be a whole bunch of CH3s. We got 3 environments. You're correct, Miguel. These are all A. This one right here would be B. And this one right here would be C. All right, let's see. So Yesenia, where would A be? Where would A show up chemical shift-wise on an NMR? Yeah, perfect. I would say that these are too far away from the carbonyl for it to have any effect, so you just go with your normal alkane, which is 1 to 1.5. All right, what about B? Right next to the carbonyl. Great. So B would be 2 to 2.5 ppm. right, what about C? Be careful. Good, yeah. So this hydrogen is not next to an aldehyde, although it might look like that way from the way I drew it, but this hydrogen is directly attached to the aldehyde. So this is part of the aldehyde and it has its own special region. We don't have a lot of those special regions, there's only 4 of them. So a hydrogen that's directly attached to an alkene is 5 to 6. A hydrogen that's directly attached to an or a benzene ring is 7 to 8. A hydrogen that's directly attached to an aldehyde is 9 to 10. And then what was the last one? It's 10 to 12. Carboxylic acid, yep. And so those are the 4 where don't worry about +1, -1, or +2, +1/4 on any of those. They just show up in that region. That's just what they are. So this one would be 9 to 10 ppm because it is an aldehyde. All right, Miguel, integrate for me. Wait, you figured out the number of chemical shifts. Chloe, what's the integrals here? 9H, yep. Yep. Perfect. Sound good? That's it? Perfect. Good job. All right, so let's practice doing some more of these in reverse. Any questions out there in Zoom? How are we doing? All right, hearing none. I assume a thumbs up. I am going to draw something for you. Let's say that we have 5 H's in a signal, and it shows up around 7.3 ppm. What does that tell us? This is our NMR signal. What can we decipher or deduce about our molecule? What environment would give rise to that stuff? Mallory, you're back up. Everybody gets chances to play today. It's lovely. So 5H is weird. Yeah. There is no such thing as a CH5, right? And there are no, you couldn't get to that with 2 whole numbers. So that being said, I would really recommend you guys start with this, but here you really can't. So let's start with this instead. What is 7.3 ppm telling you? That's one of the regions you just need to know. So a hydrogen directly on an alkene is 5 to 6. Keep going. We need a 7 to 8. Exactly. It's on a benzene ring. So a benzene ring always looks like this. How many spots are there for hydrogens on a benzene ring? Yeah, there's 6 spots for hydrogens. So in this particular signal, for this particular molecule, how many hydrogens do you have on the benzene ring? 5. So what this signal is telling you is that you have a benzene ring with 5 hydrogens on it. And do you know what this is over here? It's not a trick question. Probably a carbon is a perfectly fine answer. Is it a hydrogen? No. Do you know what else it is? No. You have no other information beyond that. So here's what we know. There is a benzene ring and it has 5 hydrogens on it. Does that make sense? So that's what that's telling you, which is a pretty good bit of information about this molecule. I'm going to make up the rest of this molecule. You wouldn't know it from the signal, but let's say that we've got like a CH2, CH3 over here. Let's go backwards for a moment to what we've been doing. This might be environment A. This might be environment B. When you look at that benzene ring, how many different environments are there really? In other words, are all of those hydrogens perfectly equivalent? No, they're not. So in a benzene ring, there's constant resonance. So the top and the bottom are completely symmetrical. Basically, these double bonds are just moving around. So we kind of treat it like this. Sometimes you draw a benzene ring like this because the hydrogens are perfectly spread out everywhere, or the electrons and the pi bonds. So from an environment point of view, these guys are identical, and these guys are identical, and this one would be by itself. But for reasons that have a lot to do with splitting, which we'll talk about on Monday, a lot of times these benzene ring hydrogens all just show up kind of stacked on top of each other. So a lot of times you can't tell the difference. And this is a lot of times what you would see is just 5 hydrogens. So while technically these are 3 different environments, they usually show up kind of on top of each other, and it's often hard to differentiate. So you didn't need to, though. You got 5 hydrogens on a benzene, you don't need to figure out where they are. There's only 6 spots, so there's just 5 H's there. And then 1 spot that doesn't have an H. Does that make sense? All right, let's keep going. We have something that integrates to 3H, and it is showing up at 3.14 ppm, because I love pi. All right, Yesenia, what does this tell us about a possible environment looking at it from a structural point of view? Yep. So this is telling you that you are a CH3. Perfect. What? No, go ahead. Okay, be more specific. Yep. So it is next to an O or an N or an X. Do you know which one? No, you don't. So I would caution you against guessing if you're randomly guessing, because it doesn't help. You are next to an O or an N or an X, and you could use something else to figure out what it is, but this signal alone would not tell you which one, and so you're done. Good job. So that's our piece of the puzzle. If this is a larger molecule, that is to say there's more signals, well, it can't be a halogen because halogens only make 1 bond. So that would mean if this were a halogen, that would be the entire molecule. But let's say that we have only one other signal in this molecule, and it is a 1H that's actually a little bit broad, showing up at, let's say, I don't know, 2.5 ppm. All right, Miguel, do you have anything in your notes about a broad singlet? You might not, and it's okay. Okay, so you probably do have in there that there are 2 times that you have something that shows up from a hydrogen in NMR that's not a CH. They are an OH or an NH. OHs and NHs are really difficult to nail down because they are not very clearly defined in terms of their chemical shift. Okay, so anybody got where an OH shows up? 2 to 7. So that's not super helpful because the scale only really goes from, I mean, it starts at 0, but nothing's at 0, from like 1 to 12. And so it's kind of anywhere. The biggest tell, go ahead. Yeah, no, 1.5 to 4, which is still a huge region. So it's really difficult to tell. But here's what I can tell you about NHs and OHs. They're always gonna be 1 hydrogen for an OH or 2 hydrogens for an NH. And there's stuff that we'll get to on Monday about splitting that's gonna be helpful as well. But most of your peaks tend to be pretty sharp. It's a lot like IR, where the CHs were pretty sharp, but the OHs and the NHs were broad. The OHs and the NHs end up being pretty broad here too. So based on this alone, it's pretty tough to tell. But if you see only 1H, it's probably slash possibly an OH. And this is, if the only peaks you had in this molecule were this one and this one, it's pretty easy to put them together. That would mean that your molecule is a CH3 next to an O with an H on it, or methanol.
This is why you should rule out halogens to hold it.
Correct, well, exactly. So a halogen wouldn't have any more H's. And this right here is an entire molecule. There are no more bonds, so there are no more H's, and that would be the entire. Alternatively, IR would let you know whether you have an OH or an NH2 or a halogen. Mass spec would tell you if you had a halogen, or it would tell you a nitrogen because the mass would be off. And then oxygen by a process of elimination. So if you have this peak right here and nothing else, you don't have a lot of information. But if you have this peak and some other information, you can usually figure it out. All right, let's do, let's say we have a peak that integrates to 6 H's and they're all around 1.31 ppm. This is a little bit trickier, but we can do it. Chloe, you're up. Good news. So let's start with what you are, not what you're near. You are 6 H's. What could you possibly be? Yep, perfect. 2 identical CH3s. Probably that means they're on 2 ends of the molecule that's completely symmetrical, or 2 parts of something that are attached to the same thing. You don't know, but they're 2 identical CH3s. Does 1.31 ppm tell you much information? Yeah, it's not really near anything meaningful. So this is pretty much all you could do. Maybe it's 2 doors down from a carbon-containing functional group, or maybe it's not, but this is all you would know. 2 identical CH3s, not next to anything fancy. Sound good? So here you just have a lack of information, but it's still something. All right. Ooh, I guess we have maybe time for one more. Let's do this. Let's do a 3H. Let's do a 2H. 2H at 2.41 ppm. All right, Timothy. What do we got?
So it could be a CH2.
Yep. So it is a CH2 for sure.
And it's probably near whole bunch of things. So it's gonna be like +1. Already.
Exactly. Yes.
Okay.
I don't know if you guys can hear him out there in Zoom, but he said it's definitely a CH2 and it's next to one of a lot of things, and it's the things that are +1. So what do all those things have in common?
It's a hydrogen attached to a carbon, alkene, alkyne.
Yep.
Where did we say the ring? Is that a ring?
A benzene ring. Yep.
Benzene ring, okay.
So a ring itself is not fancy in terms of spectroscopy.
Okay.
A ring is just an alkane that's been turned into a ring. They all just look like alkanes, except for benzene rings. Benzene rings are very different. They're their own specific function. All right. And then the other thing was a carbonyl, which you wouldn't know by looking at it structure-wise, whether it was an aldehyde or a ketone or an ester or anything like that. But what all of these things have in common is they're all carbon-containing functional groups, meaning they're the functional groups that have carbon. They all have about the same effect. So if you want to, you can even summarize this if you know what this means into carbon-containing functional groups, CZFG. Just toss them in a pot. So there's kind of 2 pots of functional groups when it comes to shifting. O and N and X are that +2, and all of those carbonyl containing or carbon containing functional groups are that +1. So technically these are all different by a little bit, but they're all roughly gonna have the effect of +1. So I'd rather you just toss them in one pot. Instead of knowing 4 specific pots, just have one general pot and be pretty good with that. And then there's 3 more, toss them in your second general pot, you only have 2 pots. So do you know which one it is?
No.
You don't, correct. You do not know what it is. Based on this piece of information alone, that is all you know. Okay, do you know what's over here? Because there has to be something else attached to a CH2.
Just hydrogen.
It's not a hydrogen, otherwise this would be a CH3.
Oh, no.
But no, you don't know what's over there. I mean, it could be a CH or a CH2 or a CH3, but it's probably one of those things. So what we will do on Monday, the 4th aspect of a hydrogen NMR, besides number of environments, chemical shift, and integral, is that these things have splitting. These signals will have splitting, and the splitting will tell us how many hydrogens are on neighboring carbons. So it gives us even more information about how to put these molecules together. So we will be doing a lot of the same stuff on Monday, but we'll be adding one more layer to it, thinking about splitting. Thanks. Have a great weekend. I'll see some of you in lab on Monday or Tuesday. Otherwise, I'll see you sometime.